Good morning, students. I hope you're having a great day. I have loaded some files to your Canvas account, so I've put some notes over orbital mechanics, and I have also uploaded the first orbital mechanics assignment. And I would like to complete the first problem with you on the assignment. So let's go ahead and get started. A 15,000 kilogram satellite is orbiting 800,000 meters above Earth's surface. How much gravitational potential energy does the satellite have? So let's go ahead and create a column of knowns and unknowns here. So the mass of the satellite, 15,000 kilograms. Our altitude, so the satellite is 800,000 meters above Earth's surface, so altitude. And the variable that we're going to use to represent altitude is d sub 0. So 800,000 meters. And it wants us to calculate the amount of gravitational potential energy that the satellite has. And gravitational potential energy is identified by capital U. But at this point, we don't know what it is. So let's go ahead and draw a simple picture to represent our situation. So here we have the radius of the Earth, identified by r sub e, and then we have the altitude of our satellite, identified by d sub 0. Now, whenever we calculate the gravitational potential energy, we're needing to take into consideration the center to center distance. So our gravitational potential energy is from the center of the satellite to the center of Earth. And this is going to be identified as capital R. Okay? Now, the equation that we're going to use to calculate gravitational potential energy is U equals minus the universal gravitational constant multiplied by mass of the satellite multiplied by the mass of the Earth divided by the center to center distance identified by capital R, which we've identified right here. Okay, now the reason that this value is going to be negative is because our gravitational potential energy vector is pointing to the center of the Earth, okay? So if the satellite is above our head, the vector is pointing down to the center of the Earth. All right, so let's just go ahead and fill in some values. So I have U is equal to negative. My universal gravitational constant is 6.67 times 10 to the negative 11th, and my units are meters cubed per kilogram second squared. We're going to multiply this by the mass of the satellite, which is 15,000 kilograms. And then we're going to multiply this by the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. And we're going to divide that. This is 5.98 times 10 to the 24th kilograms. We're going to divide this by R, which is the sum of our altitude and the radius of the Earth. So d sub 0, this is our altitude of 800,000 meters plus the radius of the Earth, which is 6,378,000 meters, okay? And so what I want to do here is take a look at my numerator, and I want to get the numerical value first, okay? Then we'll talk about the unit value. So let's go ahead and take out our calculator. So this value here, on my calculator, how I'm going to enter it, I have a TI-83. I'm going to enter 6.67, and I have to hit the second function key. and the comma, which is going to be the EE button that represents times 10. And then it's to the negative 11th. I'm going to multiply this, so times, and then I'm going to hit the open parentheses button. 15,000, close parentheses, and I hit enter. So I'm just taking care of these two values. I'm taking the product here first. Then that answer I'm going to multiply by the 5.98 times 10 to the 24th. So 5 times open parentheses 5.98, second function, so I can do the EE, which is times 10 to the 24th. Okay, and I'm going to get a negative. Remember, we have a negative up here, so negative 5.98299 times 10 to the 18th power. Okay, now let's take a look at our units. Okay, so right here I have meters cubed per kilogram times second squared times, I have a kilogram times a kilogram, which is going to give me kilograms squared. And algebraically, I can write that kilograms squared over 1. So we're going to have one of the kilograms cancel out. So in my numerator, I'm left with meters cubed times kilogram over second squared. In my denominator, we're just going to add these two values. Remember, in my denominator, I have this variable r, which is the center to center distance between the satellite and the Earth. Okay? So right here, 800,000 plus 6,378,000 gives me 7,178,000. And meters plus meters, we're in units of meters. So our gravitational potential energy, let's go ahead and divide these values here. And I get 8.335, and that's negative 2 times 10 to the 11th power. Now let's talk about the unit value. So right here are the units. Remember, when we divide fractions, it's like multiplying by the inverse of the denominator. So I have meter cubed times kilogram divided by second squared times the inverse of our denominator here, which is going to be 1 over meter, which one of the meters is going to cancel out, leaving me with meters squared in my numerator. So if I rearrange the numerator here, I get kilogram meters squared, and then we're dividing this by second squared. So if I factor a meter out of this, I get kilogram meter per second squared times a meter. And we know that a kilogram meter per second squared is a Newton. And we know that a Newton times a meter is a joule. So our final answer, our potential energy, our gravitational potential energy identified by capital U is negative 8.3352 times 10 to the 11th joules. Right there. Okay? If you have any questions in the assignment that I've uploaded to your Canvas account, please let me know. I hope you have a wonderful day.